I'll note that in the preceding I apparently used the wrong length in calculating the number of radians per second. The length of the pendulum is 40 centimeters, and I apparently calculated it based on 160. So that the omega should be 5 radians per second. That really doesn't change much in the preceding problem. We simply have determined that x of t is 3 centimeters times the cosine of omega t, theta naught 0, a, excuse me, is 3 centimeters, and omega is going to be 5 radians per second. Now that's going to be relevant in the second problem, and I used that throughout the problem when we did this in class. So let's modify this. Okay, so the second problem, or second bullet actually, on the problem number 1, tells us that we have an initial velocity of 20 centimeters per second, and that occurs when we have the pendulum hanging at equilibrium and somehow give it a 20 centimeter per second initial velocity. We have to take those two conditions. It's at equilibrium at t equals 0. It's suddenly moving at 20 centimeters per second at t equals 0. And that might not be sudden. It might have been released from here, but the clock not started till here. One way or another, it's moving at 20 centimeters per second, and that's plus 20 centimeters per second as it passes through its equilibrium position. How are we going to handle a condition on an initial velocity? Well, we have the position function. We could easily get the velocity function. All we have to do is take the derivative of the position function. So we get velocity. Well, the derivative of this function is what? We're going to get an omega from the chain rule. We're going to have a negative sign of quantity omega t plus theta naught. And of course we have our a, so our velocity function is a negative omega a times the sine of the quantity omega t plus theta naught. So that now we can say, well, v of 0 is 20 centimeters per second. If we plug 0 in for t, we get a times the sine of just theta naught, because the omega t is going to be 0 if t equals 0. And we have this equation then, omega a sine of theta naught equals 20 centimeters per second. The other is x of 0 has to equal 0. Well, x of 0, if we plug in 0 for t, we get a just cosine of theta naught, so we have a cosine of theta naught equals 0. We have then two simultaneous equations. This one, omega a sine of theta naught equals 20 centimeters per second, negative omega a sine of theta naught. A cosine of theta naught equals 0, and I really don't have to read that to you. From the second equation, we can immediately determine something about theta naught. If a cosine of theta naught is 0, then we can divide both sides by a. Cosine of theta naught is going to be 0. If the cosine of theta naught is 0, well, for what angles is the cosine 0? Look on the circle, think of the projection onto the x-axis. The only two angles that project down onto the only two positions that project down onto the x equals 0 are the 90 degree and 270 degree, that is the pi over 2 and 3 pi over 2 radian angles. So theta naught is going to be one of these two. We'll figure out which one here in just a minute. Now we're going to move on up to the top of the board here. So one of our equations is omega a sine of theta naught equals negative 20 centimeters per second, just the same as this, except I multiplied through by negative 1 to make this positive, and that makes this negative. And then solving this equation for a, we get a equals negative 20 centimeters per second over omega times the sine of theta naught. Now by convention, the amplitude is the radius of the circle, the reference circle, and the radius of the reference circle can't be negative. So we're going to make the convention that a is positive. Omega we've chosen as positive. Well, the square root of g over L is positive. So omega is positive, a is positive. Our initial, well, our negative 20 centimeters per second that we get from this rearranged equation, the one where we multiplied through by negative 1, well, that's negative. So this is negative, this is positive, and this is positive. What's this got to be? This has to be negative. if this was positive, then we'd have a negative on this side and a positive on this side. So A is positive by convention, omega is positive because that's the way it came out. That implies that the sine of theta naught is negative. Now we can choose between pi over 2 and 3 pi over 2. And our choice is going to have to be the one that makes sine of theta naught negative. That would be the 3 pi over 2, because the sine of 3 pi over 2 is negative 1. Sine of pi over 2 is positive 1. So theta naught is 3 pi over 2. Our omega is about 5 radians per second. That's not exact. And when I wrote it down here, I should have written that as approximately equal. But that's good. I think that's good to a couple of significant figures at least. Okay, so omega is about 5 radians per second. Then we can complete the solution for A. We know theta naught is 3 pi over 2, so sine theta naught is negative 1, so that negative 20 centimeters per second over sine of theta naught is negative 20 centimeters per second over negative 1, 20 centimeters per second. And then that's just going to be over omega, which is 5 radians per second, and we solve very easily. We get A equals 4 centimeters. Knowing that A equals 4 centimeters, we go back to our equation of motion. We have determined A to be 4 centimeters. We've figured out that theta naught is 3 pi over 2 radians. We plug those in, and here's our equation of motion. We can graph this equation of motion, x versus t. X can be at most 4 centimeters because the cosine can be 1 but no greater. And it can be as little as negative 4 centimeters because, of course, the cosine can also go down as far as negative 1. So we have basically a sine curve. I mean, it's a cosine, but we got that 3 pi over 2 there, and once you start shifting these things, they're all sine graphs for the right value of theta naught. But if you prefer to call it a cosine graph, okay, it still looks like a sine curve. Well, there's the graph, and if we understand how to graph cosine functions, we've got it. We just need to know what the scale of the graph is, okay? It's going to be an oscillation between negative 4 and 4 centimeters. We want to maybe label this point at least on the t-axis, and then maybe we'll label some more. Well, it turns out that this is 1.25 seconds, this point here. It takes 1.25 seconds to complete a cycle, to go from equilibrium to maximum positive displacement, back to equilibrium to maximum negative displacement, and back to equilibrium, so that we can then repeat the entire cycle. The period, capital T, stands for the period of motion. It's the time required. Well, let's go back to the reference circle. It's the time required to complete a cycle of the reference circle. Because, of course, well, it's the time required to complete a cycle of the reference circle. This reference circle doesn't necessarily apply here. I haven't drawn the reference circle for this one. We'll get that on the next one. The reference circle, wherever we start, to complete a cycle, we have to go through 2 pi radians. We're moving at 5 radians per second. That 2.5 sneaked in there. But it's 5 radians per second, so that to go through 2 pi radians takes 2 pi over omega, 2 pi over 5 radians per second, 2 pi radians over 5 radians per second, which gives us 1.25 seconds. So at 5 radians per second, we're just saying it takes us 1.25 seconds to complete the 2 pi radians of a cycle, so the length of the cycle is 1.25 seconds. We could label this point 0.625 seconds. We could label this one, what would that be, 0.3125 seconds, and so forth. Or we could do some other labeling of the t-axis. I really can't let this one go without the reference circle, so I've rearranged a couple of things over here to sneak one in. It'd be better to have the reference circle over here where we can draw the projection. very directly, but here's our reference circle. It has a radius of 4 centimeters because it comes down to here and it comes up to here. So the radius is 4 centimeters, and the r of 0 position is at 3 pi over 2 radians. Now how does that accomplish the goal of a motion that starts here and moves to the right before coming back and moving to the left? Okay. We're at the 3 pi over 2 position. Our r vector is at 3 pi over 2, and omega is going to be taken to be positive, so we're moving around the circle in this direction. So if at t equals 0 we're here and we're moving in this direction, then the projection of this r vector on the x-axis is 0 at t equals 0, but then as we start moving around the projection, it becomes positive, so we move to the right, out to the 3 centimeter mark. Now, what's the graph tell us? It tells us that at t equals 0, we start at the 0 position, and we then move in the positive direction until we get to the 4 centimeter mark. Then we turn around and come back down, and that's exactly what will happen here. The r vector gets around to here, and now it swings through this half circle, and the projection of the tip of the r vector goes to the left. Okay, so it goes in the negative direction, ends up at negative 3 centimeters, negative 4 centimeters. That corresponds again to this part of the diagram. Then we move around through that last 90 degrees or pi over 2 radians, and we're again moving in the positive direction, but we're still on the negative side where our x value is negative, but we're moving in the positive direction. Well, here our x value is negative. It's negative 4 centimeters as indicated here, but now it's going to come around here up to 0, and then we're going to repeat the cycle again because we're going to be back at our starting point, and the whole thing's going to go going to happen again. It's going to repeat. It's going to keep repeating as long as this motion is in effect. Okay, so there's an interpretation, and there's a correlation with the reference circle.